Great. Thanks, Mario. Thanks, Mario. Thanks again for having me here. I'm excited to talk to a different group of people than I normally talk to. Because of that, I'll probably say things that don't make sense. So please ask questions and stop me whenever. I'm happy to divert. Let's see. I haven't used my iPad in a very long time. Single page. There we go. All right. Good. So yeah, the title of the talk is Nielsen, Thurston, and Thurston a la Bears. This is joint work with Jim Belk and Belk and Winarski. And the summary is on this slide. So there's two theorems. The Nielsen-Thurston in the title refers to the Nielsen-Thurston classification theorem, which is a canonical form for surface homeomorphisms. I will tell you what that is or remind you what that is in a moment. That's theorem number one. Theorem number two is what's often called Thurston's theorem, although it's also called the Thurston's characterization of rational maps. And that gives you a canonical form for a different kind of map of surfaces, namely a branch cover of surfaces. And what we do in our paper, which is on the archive, is to show that these are really one theorem. You can state, not only can you state one theorem that proves both at the same time, but you're really just giving one proof, and both of these important theorems come out of that proof. Okay. All right. And as a consequence, we kind of tie up some loose ends, and I'll explain that later. Okay, so first I'll explain the Nielsen-Thurston theorem. This is the classification theorem for surface homeomorphisms. The context here is a surface, and I think for this talk, we can take a surface to be a closed surface with marked points. Okay, so compact, no boundary, some finite collection of marked points. Okay, G here is the genus, and P is the set of marked points. Okay. All right, so that's the surface of genus 3 with 4 marked points. And I'm just going to tell you the theorem here. This is it's called the Nielsen-Thurston classification. It builds on work that Nielsen did in the middle of the 20th century, and Thurston both came up with the statement and the proof. So what we're studying here is homeomorphisms of a surface, and it can be a surface with marked points like this. And it's a classification up to homotopy. Okay, so option number one is that it's periodic. Okay, that just means some finite power is the identity. Number two is reducible. Reducible means there's a collection of simple closed curves, these curves here, that are fixed by the homeomorphism. Okay, so I'm starting with a homeomorphism. I'm replacing it with a homotopic one that has one of these properties. And the last one is the most complicated to state, but it's not so complicated. The last one is called pseudo-Anosov, and it means that there's two foliations on the surface, like here. The foliations are the purple one and the, I don't know what color that is, other color, salmon or something. And so you have two foliations on the surface, and they're measured foliations, so you have a notion of how long each of these lines is. And the pseudo-Anosov map has the property that the foliations are preserved, and the surface is stretched along one foliation, contracted along the other foliation. So that's why this square gets taken to a very long and skinny rectangle with respect to the foliation. So that's what a pseudo-Anosov map is. I want to emphasize, well, okay, let me say a few things. One thing about pseudo-Anosov maps is, if it sounds mysterious, it's something that's pretty familiar from freshman linear algebra. Okay, in freshman linear algebra, we study matrices like 2 on 1, 1 acting on the plane, or the torus, if you like. And what we usually say in linear algebra is there's two eigenspaces, one with a lambda eigenspace and a lambda 1 over lambda eigenspace, since the determinant is 1 here. And you're stretching and contracting along those eigenspaces. But really, what we should tell our freshman linear algebra students is there's two foliations of the plane, and they're both being preserved, and you're stretching along one and contracting along the other. So you can think of 2 on 1, 1 as acting on the plane or the torus. It's stretching and contracting two foliations, and a pseudo-Anosov map of a surface is the same idea, just on a higher genus surface. The word pseudo refers to these singularities, and for Euler characteristic reasons, we need to have, we can't have foliations on a higher genus surface without singularities. Okay, so the singularities can look like this or look like this. This is called a three-pronged singularity. This is a one-pronged singularity. Okay, so there's still more to say about this slide, so I won't jump ahead right now, but any questions on anything I've said here? Or not said? Okay, just jump in anytime. The way that I like to think about this theorem is what's said over here. If you have so you should think of periodic as being geometric. Okay, it's something rigid like a rotation, or you can think there's a complex structure being preserved, or you can think there's a hyperbolic metric being preserved. So I should think of this as being geometric. And we should think of this as also being geometric. There's all this structure preserved. And we should think of number two as, saying you can break up your homeomorphism into pieces. And by applying this theorem inductively, you see that every homeomorphism breaks into pieces that are geometric. So that's another way of stating the theorem. Every homeomorphism up to homotopy, you can break it into pieces, and the pieces are geometric, meaning either periodic or pseudo-Nassau. Okay. Okay, so any question on that? Okay, well, I'll keep going. Okay, the next theorem is Thurston's theorem, or Thurston's characterization of rational maps. These are the two theorems I want to kind of put together. The context here is, instead of homeomorphisms of a surface, the context is branch covers of a surface over itself. Okay, so here S is a surface with some number of marked points, and F from S to S is a branch cover. Okay. Now, for this to work for Euler characteristic reasons, G can be at most 1. So to have a branch cover of a surface over itself, you can only be a torus or a sphere. Okay. We require that this set of mark points P contains the post-critical set. So when you have a branch cover, there's some points that are critical that are mapping with degree bigger than 1. And the forward image of that is a post-critical point or a critical value, and all forward images as you iterate the map, that's the post-critical set. All forward images of critical points, but not necessarily the critical points themselves. And so we need the post-critical set to be contained in P. We need F of P to be contained in P. And we usually assume that the number of mark points P is finite, although you could also consider a more general case. If P is equal to the post-critical set, then this second thing is automatic. F of the post-critical set is contained in the post-critical set. Any questions on the definition up here? Okay, so 2 examples or 3 examples maybe. The first one is Z to the D. There, the surface is the Riemann sphere, or I'll just say, actually, the whole point here is to think about maps topologically. So I won't say Riemann, even though I wrote Riemann sphere here. You should think of it as the 2 sphere. And there's these 2 post-critical points, 0 and infinity. That's where the branching is happening. They map to themselves. That gives you this portrait. So you have these 2 critical points that map to themselves with degree D. So this down here is called the portrait. It's recording that information. And it has all these properties. There's 2 points in the post-critical set. It maps to itself. It contains the, P. Yeah, if this is P, it contains the post-critical set. It equals the post-critical set. Example 2 has no critical points. That's why I wrote the empty set here. And it's just a higher degree map of the torus. So the determinant of this matrix is 6 is 2. So this is a degree 2 map of the torus to itself. P is empty. And the third example is the sphere with 3 post-critical points. And the map is Z squared minus 1. And we see here that infinity maps to itself with degree 2. The point 0 maps to the point -1 with degree 2, and -1 maps to 1 with degree 1. And so here, the set of mark points is the post-critical set. So we have both of these things. This is finite. and we have a branch cover. A branch cover, you should just think of it as when you delete the mark points. If you delete the mark points and their pre-images, you get a covering map. Okay, so this is the setting of dynamical branch covers. The first theorem I talked about was about homeomorphisms of surfaces. Thurston's next theorem is about these maps, which you should think of as topological objects. Okay. All right, any questions? Let me know. And to state Thurston's theorem, it requires one more definition, or maybe a couple more, I don't know, of exceptional maps. And this isn't the usual terminology in the literature, but for us, this makes sense, and it'll maybe be clear later. So for the torus, a torus comes equipped with a hyperelliptic involution, which is just rotated by pi. It's also, you can think of it as multiplication. It's the matrix negative I acting on the torus, negative the identity. And the quotient is a sphere with 4 marked points, the 4 marked points being the images of these 4 fixed points. And a homeomorphism, a branch cover F of the torus to itself descends to a branch cover of the sphere with 4 marked points over itself. And when the degree is bigger than 1, both of these maps are called exceptional. So in other words, exceptional maps for us are either higher degree maps of the torus or the corresponding map you get by quotienting by the hyperelliptic involution. And every linear map of the torus commutes with negative the identity, so it descends. So in the literature, you might, if you've seen this topic before, you've seen like hyperbolic and parabolic orbifolds. For our context, these are the special ones. It's just a different phrasing. Okay, so exceptional maps are quotients of torus maps by the hyperelliptic involution. Okay, so now we can state the theorem. This is Thurston's theorem. It's maybe better called Thurston's characterization of rational maps. And so you have a branch cover of a surface with, and this should really be a 2-sphere for it to be. You have a branch cover of the 2-sphere over itself with some set of mark points. Then either it's rational, meaning for some choice of identification with the Riemann sphere, it's a rational map, which is the same as being a holomorphic map, or it has what's called a strong reduction system. And I haven't told you what that is yet. The usual statement of Thurston's theorem is that either you're rational or you have a Thurston obstruction. But we have a reason for not using that terminology, which I'll explain in this talk. And in the non-exceptional case, these are exclusive. Okay, so there's this very special kind of map you get from taking a torus map and taking a quotient by the hyperelliptic involution, except in that case, either you're rational or you have a strong reduction system. All right, so this is a way of, so again, you can think of this, well, right, so it's an either or, either irrational, which is the geometric kind of map, or there's something like a reduction system. All right, any questions on that statement? Okay. So Thurston proved this in '83. The details, I think, appeared 10 years later in a paper of Doherty and Hubbard, and there are a lot of details to work out. Okay, so what is a strong reduction system? Here's the definition. So if I have a branched cover of a surface over itself, and if you want, you can think of the 2-sphere here, because it's either the 2-sphere or the torus. So it's a 2-part definition. First, I tell you what a stable multicurve is, and then I tell you what a strong reduction system is. So M is a multicurve. That's a collection of curves in S. So M is these 2 curves here. And I've drawn it suggestively for a reason I'll explain later. And they're just multicurves, so a collection of disjoint curves. And stable means the preimage contains the original multicurve. So the preimage of this green curve down here is these 3 curves maybe, and the preimage of this pink curve down here is these 2 curves. And you can see the preimage contains the original curves, at least up to homotopy, or isotopy, which is all we care about. So that's stable. That's I think a classical definition. So that's the usual thing. This definition is not classical. So a strong reduction system means you have a multi-curve, but you put labels on the curve. So I'm just putting numbers 6 and 1 here. Okay. And strong reduction system means when you take the pre-image contains M as labeled multi-curves. What does that mean? That means you have the same curves plus extra curves, and the labels are at least as big on up here as they were down here. Okay. So this containment is two things. It's containment of multi-curves in the usual sense, but also the labels up here are at least as big. But there's another catch, which is that the labels have to change in some way. So since this diagram is telling me that this curve is mapping to this curve with degree 2, right? Whatever the degree of this map is, each curve might map to, the curves might map to each other with different degrees locally. So this curve is mapping to this curve with degree 2, so that means I divide the number by 2. That's just the rule. Okay. And the rule has to do with moduli of annuli, which I'll talk about in a little bit. Okay. So F inverse of M, it should really be like F star of M. You pull back curves that also change the labels by these local degrees. So this curve is mapping to this one with degree 3. So that's why I divided the 6 by 3 and I got a 2. And let's say this curve is mapping to this curve with degree 1, like this arrow here. So this 1 pulls back to a 1. And then I have to do another operation, which is, add these two curves together and turn that into a 3. Okay. So it's kind of a complicated procedure, but if you know about moduli of annuli, that's what you should have in the back of your mind. Any questions on this definition? I'm not done with this slide yet, but any questions on this definition? I packed a lot into a small amount of notation. Okay, so the next question is, where is there a strong reduction system in this picture? Okay, the two, if you take the union of the two curves downstairs, that's a multi-curve, right? You could take M to be this. That's not a strong reduction system, because when I go up, I have this curve, but it only has a 3 on it. Okay, and this containment means the labels upstairs should be at least as big. So what are my other choices? So this curve by itself is not a strong reduction system. The two curves together is not a strong reduction system, but this curve by itself is a strong reduction system because the pre-image is just the same curve. Well, it contains the same curve with the same label. So the only M that works here is this, just this curve. Okay. And I'll explain in a moment. This has to do with, this is what happens, why this weird rule with dividing the numbers. That's because that's what happens to moduli of annuli. If you have an annulus of modulus 6 and you take a degree 2 cover, it becomes an annulus of modulus 3. Okay, and if you have two annuli of moduli 2 and 1 next to each other, they form an annulus of modulus 3. So we're recording that kind of behavior. Okay, and the theorem, I'll put it up again in a second, but the theorem said that either you're rational or you have one of these. And so the point is, these strong reduction systems are supposed to be poisoned for being rational. And I'll explain in a second that, the basic reason is moduli are supposed to get bigger when you apply a rational map. And here, moduli are getting bigger when you go up. That's the idea. There's no moduli here. This is just topological.
But then a quick question. At the end of the day, I guess you want to have a kind of contradiction to Grudge inequality, or?
Yeah. No, not. Yeah. Yes. So I have a slide for that. So, yeah, that's right. I'll explain why this obstructs rationality or holomorphicity in a second. But it's some kind of Grudge thing. But there's another deep thing you need, which I'll say in a second. It's on this slide. So, okay, why are strong reduction systems Thurston obstruct? They're not always obstructions to holomorphicity or rationality. I'm just conflating holomorphicity and rationality. So, but I'll explain that they are most of the time. So that most of the time, these strong reduction systems obstruct holomorphicity. And the basic idea is holomorphic maps increase moduli, which I said. So here's the map z squared. And so the modulus of this annulus is log r just by definition. And if I apply z squared, it becomes this annulus. And when I take logs, it's 2 times log r, it's log of r squared. And so the modulus multiplies by 2. So you should think of holomorphic maps. They make moduli of annuli bigger. Okay, and up to change of coordinates, every holomorphic map restricted to an annulus looks like this picture. Okay, so here's the heuristic for why strong reduction systems are bad if you want to be holomorphic. Okay, a strong reduction system gives you a multi-annulus with non-increasing modulus. So here you take those multi-curve with the numbers and you make annuli, and you lift them up and you're seeing annuli that have bigger modulus, and it's supposed to go the other way. That's the intuition. That's not a proof. And Mario was asking what's the actual proof here. What's really going on, I didn't write it on the slide, is there's something called the Jenkins extremal problem. Okay, so if I draw a multi-curve and I put numbers on them, I can actually fill up the whole surface with annuli, where the ratio of the annuli is exactly given by those numbers. And then when I pull back, like the strong reduction system definition says, I have even bigger moduli upstairs. But Jenkins says, wait, I've already maximized the extremal problem. So it must be the exact same set of annuli upstairs, not bigger, but equal. But because this is a degree bigger than 1 map, the area has multiplied by something. The area is multiplied by 2 or d, whatever d is. Okay, so what that means is, okay, so you're getting a metric on the surface, because you're getting a metric on the surface, or you can think of it as a complex structure that's getting multiplied by d. And so you can lift that to the orbifold universal cover. And so you're getting a whole, so you're getting a homothety of the orbifold universal cover. And so the Euclidean plane has a holomorphic homothety, right? When you scale by d, that's a homothety of the Euclidean plane that's holomorphic. But the hyperbolic plane does not have a holomorphic homothety. And so if your orbifold is what's called hyperbolic, and I'm not going into that, the universal cover is the hyperbolic plane. And so you can't have this phenomenon that areas are getting multiplied by d. Does that make sense, Mario? Any questions? Okay. So it's really, yeah, we explain this in our paper that, well, maybe it's too much to go into, but that's the idea. You really need this Jenkins extremal problem. Okay, so now Thurston's theorem is that up to homotopy, again, it's just restating, any dynamical branch cover is either rational / holomorphic or it has a strong reduction system. Okay, and in the non-exceptional case, it's exclusive. I'll explain why it's not exclusive in the exceptional case. But the whole point of the exceptional case is that the orbifold universal cover is the Euclidean plane. Now, there are other maps where the orbifold universal cover is the Euclidean plane, but they have 3 marked points, and hence there's no reduction. When you have a sphere with 3 marked points, there are no curves. Every curve is homotopic to a marked point. So there's kind of 2 special things that happen. Okay. All right. Any other questions? Okay. All right. So now I'm going to explain how these 2 theorems, how we combine them into one statement. And here's the statement. So we have a dynamical branch cover, just meaning a branch cover of a surface with marked points over itself. Then either it's holomorphic or strongly reducible, or it's pseudo-Anosov. Okay. Now, pseudo-Anosov, I've changed the definition. In the original definition for surface homeomorphisms, well, D is 1. And so I just said one foliation gets multiplied by lambda, one gets divided by lambda, where you're dividing the measure or multiplying the measure. And so I put a square root of D there, because under a degree D branch cover, area should multiply by D. So that's what's happening here. And so this combines both theorems, because a holomorphic map when degree is 1, that's a periodic map. If you have degree 1, a holomorphic map of a surface to itself, it's periodic. and holomorphic is the same as rational for the torus and the sphere. So you have that. Strongly reducible when degree is 1 it is the same as reducible, because the numbers on the curves don't change at all. So it turns out that's the same as being reducible in the sense of the Nielsen-Thurston classification. And obviously this definition, when you make D equal 1, is just the definition of pseudo-Nosov for homeomorphisms. So this is one statement. Just as it is, it's maybe just a cute combination of the two theorems, because homeomorphisms are really about higher genus surfaces, and then there's also tori and sphere, and Thurston's theorem is about branch covers of the torus and sphere. So you can combine the theorems together. What's more interesting to me is that the proof is the same. Okay, like without doing any other work, you could just combine the two theorems and have this statement. But the point is the proof gives you both at once, which I think was not realized before, but Mario can correct me if I'm wrong. And by giving this proof, we were able to extend Thurston's theorem characterization of rational maps to surfaces with extra mark points where the P is bigger than the post-critical set, torus case, non-arrangeable surfaces, equivariant maps. That's kind of an aside. That's not the main point I want to get across today. So any questions?
A quick question then. In the case where the degree is bigger than 1, this pseudo-Nosov situation, so this arises for parabolic orbifold or also for hyperbolic orbifold?
So yeah, it should not happen for a hyperbolic orbifold exactly because of the reason, because you're gonna get some homothety of the universal cover. So if you look at the paper, we say exactly when you can get overlap, and so but this picture encapsulates, and this is all happening on the torus. So let's answer your question in more detail in a second. Let's go through this. So these are all maps of the torus. By taking the quotient by the hyperelliptic involution, you can get maps, parabolic maps, meaning Euclidean orbifold maps of the sphere. So holomorphic, right? This map is a holomorphic. This map is both strongly reducible and holomorphic. Okay, it's holomorphic because it's a scaling map. It's strongly reducible because you just look at the vector 1, 0. This is maybe this curve. It lifts to itself, but the numbers get bigger when you go up, when you go backwards. Okay, because you get square root of D copies of the curve. Is that right? I'm sort of confused by that. So if I do 2, 0, 0, 2, then this curve is mapping to itself with degree 2. Oh, I see. Yeah, it's confusing, right? So you put a 1 here, okay? And then you say, wait, this isn't a strong reduction system because that's a half. But there's whoops. Key moment. But there's 2 copies of that curve in the pre-image, both with label 1/2. And so they add together to give you a 1. Okay, so that one is both strongly reducible and holomorphic. This one is strongly reducible. It's clearly not holomorphic. It's some kind of shear. But again, you have the same property, the same picture that I drew. Let's see. D001, that's a Nosov. So you're stretching just in the x direction by D. And so you have these 2 foliations, they're horizontal and vertical, and they're preserved. And, you check the formula I wrote down for, what a pseudo-Nosov is, and that's it. And the last one is a Nosov, but not reducible. And so when you make D equal to 1, this is the famous 2, 1, 1, 1 map. But notice when the degree is 1, you don't get any overlap here. This is the identity map. But that's because the Nielsen-Thurston classification says when the degree is 1, there's not supposed to be anything there. Okay. So back to Mario's question, is there a pseudo-Nosov with hyperbolic overfold? The answer is no. It's only examples like this, and it's because of that reason I said. So repeating my previous answer, but just with more emphasis. Okay. Any other questions on this slide or anything?
When you write these square roots, of course, then the d's have to be squares.
Yes. D is squares. Yeah. Why did we write it this way? Well, I don't know, just because that is the square root of the degree. But yes, so D, yeah, so I should say D is a square. Well, just in the first three examples, D is a square. Yes. Other questions? Okay, so I want to talk about how you prove both of these, all of this at once. Okay, and the proof is really so Thurston proved the Nielsen-Thurston classification in the mid-70s, and then shortly after, Lippmann-Bears at Columbia gave a proof using Teichmüller theory. And what we're doing is, well, first observing that the Bears proof proves both theorems at once, and then there's some details to work out, and some, but that's the main observation, is that Bears had a proof of Nielsen-Thurston, and we say, oh wait, that works to prove both theorems at once, to prove the Ubertheorem. Okay, so my goal is to explain the idea of the Bears proof and explain why it extends. Okay, so the Bears proof of the Nielsen-Thurston classification uses Teichmüller space. The Teichmüller space of a surface with mark points is just complex structures on the surface, okay? And you consider complex structures. Complex structures don't really see the mark points, but the point is we consider complex structures up to isotopy, or in other words, you pull back by diffeomorphisms that are isotopic to the identity relative to P. So the mark points are there they don't really factor in here, but they more factor in down here. Okay. So that's a space. There's lots of complex structures on the surface. It's easy to make complex structures on a surface with mark points. All you do is draw a polygon and identify sides. And as long as the angles at each corner add up to 2 pi, that's a complex structure on the surface. So if you glue up this L shape, according to the labels, it's a genus 2 surface. That is a complex structure. This is the map to the complex plane. The interior of that L is a chart, and the rest of the charts get kind of automatically determined by this one chart. And then you put the mark points wherever you want. If I push this mark point over here, that's going to be a new complex structure on S comma P. It'll be the same complex structure on the genus 2 surface, but it'll be a new complex structure on the marked surface.
So then a quick question.
Yeah.
I mean, when you talk about complex structure, you really think of this in terms of charts?
Good question. No, I think that's the easiest. Yeah. Yes. Oh, sorry. Yeah. Yeah, that'll be my definition for today. It's just you have charts to the complex plane, and transition maps are holomorphic. I mean, we know from uniformization that's the same as being a quotient of the open unit disk. But I think for today we can just think about charts. And so one way I can change the complex structure is move the mark points around, but I can also do something like shear. If I shear the L or modify, I can get different points in this Teichmüller space. Those are all different complex structures. On the torus, I can, I can take a square. I can take a parallelogram. That's as close to being a parallelogram, but you get the idea. That's too ugly. I could take a torus. I could take a parallelogram, and these are two different complex structures on the torus. Okay, and if I add mark points, I can push the mark points around and get different complex structures. Okay. Any questions on that? So that's a space. I mean, the topology is just the natural thing, meaning if I start shearing and changing this complex structure continuously by shearing these polygons, I'm moving around in the space. And I don't know if I wrote this on a slide, so I'll write it here. It turns out this is homeomorphic to Rn for some n. Any questions on my definition of Teichmüller space? Any other questions? Okay, so now there's a distance in Teichmüller space, meaning I can compare two complex structures and say how far apart they are. Okay, and here's the basic idea. So I have 2 points in Teichmüller space. Those are two complex structures on the same surface. I look at a map that's homotopic to the identity. And for any map of complex surfaces, of Riemann surfaces, I can talk about the dilatation, meaning the map will take a small circle. You can think of that as being in the tangent space, or you can think of it as being a small circle, and it takes it to an ellipse. Okay. So that's the dilatation of a map at a point. It's just it's how far it is from being it's the eccentricity of the ellipse. That's how far it is from being holomorphic. Okay, so that's the dilatation at a point, and the dilatation of f is the max. So it's the worst point. It's the worst stretching you have. And then the distance is just that. It's half the log of the dilatation. So, but basically you're just looking over you're looking over, well, first you have to minimize overall f. And it's not obvious that the minimum exists. That's a theorem of Teichmuller. And so you're looking at how bad the ellipses are in your map between two complex structures. And you take the best map, the worst point for the best map. Okay. And that's telling you how far apart the complex structures are. So these are two complex structures on the torus, square and a rectangle. The best map is the obvious map, the affine map, and the amount of stretching, the dilatation is the same at every point. And so you compute the distance. The more you pull the rectangle, make it skinnier, the farther you're moving in Teichmuller space. This one is more interesting. If I take the square and the parallelogram with a 45-degree angle. So the best map there is, again, the linear map. I mean, I guess maybe that makes sense. So 1101 is the best. Is that right? No, that's not right. Is it? Let's see. No, it is the best map. The best map is 1101. And so the distance, you just figure out what that's doing to circles. It's taking it to some ellipse, and I'm not sure what number you get, but it's bigger than 1. So, all right. Any questions on the distance? You're basically seeing how much you have to stretch to get from one complex structure to the other. There's a really confusing thing. I'll explain my confusion in a sec on the next slide, I think, but it's a really funny thing. Okay, so it's just the distance is just some way of measuring how far apart two complex structures are. Okay, this is the really deep thing, okay, is that you can actually compute geodesics in this space. Okay, the geodesics in the space are always, you stretch along one foliation, contract along the other. Okay, this should look familiar. This should remind you of our definition of pseudo-Anosov maps. And so obviously, I think obviously the geodesic from the square to the rectangle should just be stretch, right? Just pull it this way. What else could there be? But what's really interesting is that the geodesic from the square to the 45-degree parallelogram, right? You're trying to get from this torus to this torus. Your first guess is that the geodesic is to change the parallelogram like this until you get to 45 degrees. But that's not the geodesic. The geodesic is to expand and contract, stretch and contract by the 2-on-1-1 matrix, a power of the 2-on-1, not 2-on-1-1 itself, but a power of it, some irrational power of it. And that takes this square to this parallelogram, which is the 45-degree parallelogram, but rotated. And that's the geodesic. So for me, that's kind of mind-blowing. That's like you have this obvious geodesic, but that's not it. It's these stretch maps. It's these pseudo-Anosov-like maps. But and I wrote SVD here to remind myself to say it. I mean, this is what you're doing when you find so you should think of pseudo-Anosovs as like, eigenvalues, eigenspaces, things like that. And you should think of Teichmuller's theorem as a singular value decomposition, right? What you're doing is you're finding a map between two Riemann surfaces where you first change coordinates, and that's the foliations, and then you stretch by a diagonal matrix along those foliations, and then you change coordinates back. Okay, so while pseudo-Anosov is the analog of eigenvalues and eigenvectors, Teichmuller's theorems is the analog of SVD. Okay, so you can have the same phenomenon on a genus 2 surface, where the Teichmuller geodesics are, you choose foliations and you stretch, and just to emphasize, when you do this for higher genus surfaces, there will always be singularities just for Euler characteristic reasons. Okay, so that's Teichmuller's big contribution, is not only can you define a distance, you can exactly say what the most efficient way to get from one complex structure to another is. Okay, any questions there? And this is Bayes' observation. Like when he saw Thurston's theorem, he said, oh, those pseudo-Nassau maps look like Teichmüller maps. So I should be able to prove the theorem using Teichmüller space. Okay, so these maps are called Teichmüller maps, these best maps. I mean, the weird thing is, if you change coordinates, sorry, this is what was confusing me earlier. If you change coordinates, this is the 1101 map. Okay, it's just that so this one over here, it's just that the way you get from one to the other is not just 1T01. It's really confusing. Okay, all right. And this is why I wanted to think about charts, Mario, is I want to talk about the pullback map. So when we have a branch cover of a surface over itself, this is Thurston's idea, and this is Duoddy and Hubbard use this also. You get a pullback map. You get a map from Teichmüller space to itself. It's called the pullback map. And it's because if I have a complex structure on, let's say, the sphere, that's a bunch of charts from the surface to the complex plane. And when you have a branch cover, you can pull that back and you get charts on the cover. And so given a point in Teichmüller space, which is a complex structure down here, you get a complex structure up here. Okay, but that's the same surface upstairs as downstairs. So you get starting with the point in Teichmüller space on SP, you get a point in Teichmüller space on SP. So that was Thurston's idea for how to prove the characterization of rational maps. Okay. And I attributed this proposition to me and Becca and Jim. It's not so different from what Duoddy and Hubbard do, but it's slightly stronger of a statement, is that the pullback map is a weak contraction. Okay, so the Duoddy and Hubbard proof uses infinitesimal point of view. It's not that different from this, but this proposition says that when you do the pullback map, distances can't get farther. Okay, and in fact, when you do the square of the pullback map, you get points get closer together. Okay. And I changed terminology and I forgot to change the slide. So unless exceptional map. Is this the right color? Close enough. Okay, and do I have a picture for this? Yeah. Okay. Okay. This is the slide I was supposed to show. Okay. So, okay, why do distances not get bigger when you do the pullback map? Okay, here's the idea. Oh, I had this picture here, which I want. Let's see, cut. Okay, so this is my picture of the pullback map. There's some commutative diagram. So let's say I have 2 points in Teichmüller space. I take the Teichmüller geodesic between them, which means so here, I'm stretching along 2 foliations. When I pull back, I get a Teichmüller map up here also. So I start with 2 points in Teichmüller space. There's a Teichmüller map between them, meaning I'm stretching, contracting. When I pull back by F, I get the same Teichmüller map. Okay, so after pulling back, I still have the same Teichmüller map. So the distance looks like it should be the same. The issue is the distance can get smaller because the Teichmüller map you get up here might be a fake Teichmüller map. It might have a picture like this. Okay, and that picture is not allowed in Teichmüller's theorems. In Teichmüller's theorems, you can have a one-pronged singularity in the foliations as long as there's a mark point there. But in our setup, we might have a mark point whose preimage upstairs is not a mark point. And therefore, the Teichmüller map you had down here, it does lift to like a quasi-Teichmüller map up here. Okay, but there's an even more efficient map because this picture means you can like reduce the stretch. There's a homotopic map that has even less stretching. So you naively expect your Teichmüller map lifts the Teichmüller map, therefore distances stay exactly the same. But because of this picture lifting to this picture, you might get some unfolding of the Teichmüller map. It might become more efficient upstairs. So this is basically our main observation is this. And then we kind of have to do some work to make the rest of it go through. But this is the sort of the main point. So I'll pause if there's any questions. Right. So Teichmüller proved that you have Teichmüller maps between any two points in Teichmüller space, and those realize the distance, and it's unique. So the point is, when this pulls back to this, it's no longer a Teichmüller map. It's like a fake Teichmüller map because this point isn't marked, and therefore the unique Teichmüller map is better than this. Is a smaller stretch factor, smaller dilatation. Okay, so if there's no questions, I'll keep going. Okay, so for that argument to work, I mean, so I just proved to you that distances don't get bigger when you pull back. Why do they actually get smaller? And the point is, the short version is that you should always expect this to happen. Okay, you should always expect that when you have a Teichmüller map downstairs and there's a marked point, a one-pronged singularity, at least after taking a power, some iterate, you should expect to see this picture in the pre-image. And so that means the distance actually gets smaller, which is what you need to prove Thurston's theorem and the Ubertheorem. So there is this one kind of map, the exceptional maps, the quotients of the torus by the hyperelliptic involution, where this never happens. Here's the portrait. You have critical points that map with degree 2 to post-critical points, which then map to other post-critical points, which then map to themselves, and all these other arrows are degree 1. And so, your Teichmüller map on the sphere has to have at least 4 one-pronged singularities. So you put them here at these 4 points, and you keep taking pre-images, and no matter how many pre-images you take, all you get are these 6 points. Okay, so this, and the point is, this one-pronged singularity, the pre-image is not a mark point. The pre-image of this mark point is not a mark point, but there's unfolding, and so you don't get the bad picture on the previous slide, which looks like this, right? You never get that picture. Whenever the pre-image of a mark point is unmarked, it unfolds, and you don't get the one-pronged singularity. Okay. But it's a very special portrait that makes this work. For most portraits, you expect to have, as you pull back further and further, you expect to get exponentially more pre-images of mark points, and so you expect to see this picture somewhere. That's the argument. So this part of the proof is not so different from what Dewey and Hubbard wrote up. I think we simplify the argument a tiny bit if you look at our paper, but it's the same idea if you're familiar with that.
Well, I mean, they phrase it in terms of quadratic differentials, right?
That's right, but it comes down to this combinatorics and Riemann-Hurwitz formula.
Yeah, I mean, they do have a lemma that somehow recognizes, when the orbifold is parabolic, which essentially comes down to what you just explained, right?
Yeah, exactly. The way we simplified it is basically to say, so that if you don't care that the number is 2, so we say here that that this works, that you get contraction for k equals 2. You don't need that to prove Thurston's theorem. So if you don't care about that, the proof gets much simpler. So that's kind of our simplification. Okay. All right. So that's all the Teichmüller stuff. How does Bayes use that to prove Nielsen-Thurston theorem, and how do we use it to prove the more general Ubertheorem? And just to be clear, we're not taking credit for the theorem. We're combining those 2 other theorems. So here's what you do. Given a branch cover F of the surface to itself, tau F you define to be the translation distance. So you look at all points in Teichmüller space and they move some certain distance, and you take the infimum. Okay, so this is something you can define for any metric space, any action, any group action on a metric space. Here you should think of it as Z acting on Teichmüller space, powers of F. And there's 3 options. Either this translation distance, this infimum, is realized, and 0, it's not realized, or it's realized and greater than 0. Those are 3 options. It's either it's realized or it's not, and if it's realized, it can be 0 or positive. And what you show, well, the first line is easy. If the translation distance is 0, that means you have a fixed point in Teichmüller space, which means there's a complex structure that's fixed. That's what holomorphic means. So there's basically no content here. The content is in the other 2. If tau of F is not realized, you show there's a stable multicurve. And if tau of F is positive and realized, you show you have 2 invariant foliations. Okay, and hence your pseudo-Nassau. So I'd like to explain a little bit about how that works. Is it okay if I keep going for a few minutes more, or do you want me to stop now and take questions?
No, go ahead. I mean,
I'll go for a couple more minutes. I just have yeah, two pictures that so case two, so this is the case where tau of f is not realized. Just in broad strokes, what we do is we show that orbits go to infinity in Teichmuller space. And going to infinity in Teichmuller space, when you go to infinity, that means you're like pinching along a curve or a multi-curve, okay? And you want to show that that's a strong reduction system. And the idea is, so the fact that tau of f is not realized means you're moving off to infinity, and and you just show that if this multi-curve that you're shrinking is not a strong reduction system, that kind of means you're pushing away from that point at infinity. That means the curves are wanting to grow. So you get this tension between, by Mumford compactness criterion, you're going off to infinity. Being not a strong reduction system means the curves are getting longer as you apply f. So longer means smaller modulus, right? So longer in the hyperbolic metric, smaller modulus in the complex setting. So there's this tension between going off to infinity and not going off to infinity. So just in broad strokes, and in broad strokes, case three, this is the same picture in the Bayes proof. So you assume that tau is greater than 0 and realized, and what you show is that there's a geodesic in Teichmuller space that's preserved. Okay, you look at a point x, you look at a point, the x that realizes the minimum, you look at sigma f of x, and you show that that whole line is preserved. So you show that this can't happen. You can't have that this point halfway between goes over here. It has to go over here. Okay. And what's the reason for that? Then I guess this would be less than this, where you're assuming x realizes the infimum. And so if you have this bending, that's a contradiction by the minimality. And so it must be that sigma y is here. So this geodesic is preserved, but we said Teichmuller geodesics are stretching and contracting along foliations. And so that's what gives you pseudo-Anosov. Okay, so geodesics correspond to foliations, and that's how you get pseudo-Anosov. I think that's all I wanted to say. Right, I say the above argument shows sigma f is an isometry of this geodesic. It's really a geodesic ray, and therefore you preserve the foliations. So hopefully that gives you a good idea of what we did. So I think there's a lot to do with yeah, the interplay between these two theorems, but that's the first step. So thanks very much.
Okay, thank you very much, Dan. Let's thank the speaker. Okay, so let me open the discussion. Questions or comments? Actually, let me stop the recording, so maybe some people are